Hey, so what is equilibrium? Well, it's when the total force acting on an object is zero. Hey, notice that isn't saying that there aren't any forces acting on the object. It says that the total force acting on an object is zero. We'll see more about that in a little bit. Another way the word is used quite often is referring to an object. An object is said to be in equilibrium when the total force acting on it is zero. Why do we care about this? It turns out that if we know an object is in equilibrium, we will know something about its motion. And if you stick around and learn a little bit about Newton's laws of motion, this will come up again. We could also turn it around and say, hey, if an object moves a certain way, we know it must be in equilibrium. So it turns out to be useful for predicting motion and figuring stuff out. Well, let's just do it at some examples. If we take a look at an example of a potato, for some reason, way out into space, if we go way, way, way out into space where we can pretend that gravity really isn't acting on it, which really isn't true because gravity is a really long-acting force. But if we go far enough away, it's not very much. So we'll pretend that there aren't any forces acting on it. So here's the potato. There, potato. And if we ask what forces are acting on it out there, there aren't any. So there's no one coming up and pushing the potato. There's no like leash attached to the potato and pulling it along. The potato isn't magnetic, and we've put a large magnet next to it. And we're pretending that we're far enough from any object that gravity isn't an issue either. So in this is kind of an unusual situation. There's no actual forces acting on the potato, to a good approximation. Therefore, the total force is zero. If I wanted to be really, really more careful about this, I could, instead of using the equal sign, I could use the approximate sign. F total is approximately zero, but we'll pretend it's zero for now. All right, so in that case, the potato would be in equilibrium. And it turns out, if that's the case, we could actually say something about what we would expect it to do with regard to how it moves. Let's look at another example. What about a potato? Yes, the potato theme. I don't know why it struck me as funny at the time. About a potato sitting on the counter in your kitchen. So here's the counter in your kitchen. Beautiful. Here is the potato. Beautiful. And the potato is just sitting there. And what forces are acting on it? Well, if you thought gravity was acting on it, that was fairly clever of you and correct. We've got gravity acting down. And if you've been following these tutorials or just know about it already, we know we can represent forces with vectors, which is what I've drawn with the arrow. So we know gravity is acting down like that. Let's pretend that the force of gravity on this potato is 7 newtons. Is that the only force acting on this potato? Well, no. The counter is actually pushing up on the potato as well. So if I were to draw the vector representing the push of the counter, I'd have to draw it straight up. And if it's also 7 newtons, which it is, then I'd have to draw my vector up, hopefully about the same length as the vector that I've drawn for the gravity. So F counter is also 7 newtons. So here's where I get to slip in a little bit about how you add up vectors. I've got 2 7 Newton vectors acting on this potato. What do you think the total force is? Now, part of you probably wants to say 14, and another part of you probably says, wait a second, they're in opposite directions. Don't they kind of undo each other? Well, your second thought is correct. In math class, when you're just dealing with straight numbers, 7 and 7 was 14. But when what you're adding are vectors, direction matters. So you kind of need to think of one as positive as one as negative, and we could be more careful with that. But right now, it's pretty obvious. One's in one direction, one's in the other. F total equals 0 again. So up in space, we had a total force of 0 simply because there were absolutely no forces about acting on the potato. In the second example, sitting on the counter, there are forces acting on the potato, but they balance each other. That's a good word to have rolling around your little brain cells near your equilibrium brain cell. If all the forces are balanced, then the total force will be 0. And let's look at another example. This time, let's take a truck of potatoes driving down the highway. So here we have a lovely truck of potatoes. Oops. The Spud truck. Wheels. Trucky looking thing. There we go. So we have our Spud truck going down the highway. And if we ask, well, what forces are acting on this? If we assume that the truck is going at a constant velocity, we know something about the forces. Well, let's see. Let's give ourselves a road. And now, if I draw the forces acting on the truck, we can imagine that gravity is acting down. And maybe it's 1,000,000 newtons. I kind of made that number up. I don't know if that's very realistic or not. Probably not so bad. Well, if the truck is staying on the road, not floating up in the air or not getting buried into the road, then we know the road must be supporting the truck exactly the same amount in the up direction. So the force due to the road is 1,000,000 newtons. And that's, if we stopped right there, that looks a little bit like the potato problem when it was sitting on the counter. But if you're driving the truck, you know that you probably have your foot on the gas pedal, keeping it at a constant velocity, the truck. And we know that somehow, without getting into too much of the details, we know the engine is somehow making the truck move forward and is providing a force on the truck. So it turns out that it's friction of the road pushing on the wheels that make the truck go forward. But for now, let's keep it simple. And let's say that the truck's engine provides a force of, let's call it 400,000 newtons in the forward direction. Well, there actually is lots of other force acting on this truck as well. If you stuck your head out the window of this truck, you would feel a lot of air against your face and your lips would flop all over the place and all that kind of stuff. It'd be pretty fun. There's also just all that resistance, rolling resistance and friction of the wheels. And it turns out that one possibility is that all that resistance and friction force is exactly equal to the engine's force forward. So if we say F, we'll call it resistance here. That could be a combination of air resistance and friction and all that stuff. And let's say that equals 400,000 newtons. So if we look at this situation, there are lots of forces, vertical forces, horizontal forces acting on this truck. But if the situation was, as I've shown you here, notice what happens to all the forces. The gravity force and the road force completely balance each other up and down, so there's no total force up and down, and the engine's force and the resistance due to air, resistance, and friction also balance each other. So again, the total force in this situation is 0. 0 newtons. And because of that, we actually could say something about how this truck is moving, but that's not the point of this tutorial. So we've got no forces at all, total force is 0. Hey, two forces that completely balance each other while the little potato is sitting still, total force is 0. We got a truck, 4 forces acting on it, up, down, either way. It's actually moving too, but we still say the total force is 0. Can that really happen? Can you have a total force of 0 and have something be moving? Yes, you can. Let's see. Last example. What was I thinking? Oh, yeah. Okay. What if I don't know why I included this. Why not? So now we have a potato again. Potato with a hat on. That's a hat. And on skis. That was a ski. There's a ski. Not sure how the potato is skiing exactly, but it is. So if it's on the flats, that means it's already come down the hill, it's cruising along, maybe heading over toward the lodge or something like that, and it's a good ski day. So in this case, you got the snow. What are the forces acting? Well, should be pretty easy so far. We've got gravity again, F grav. Let's call it, I don't know, 10 newtons. A little heavier with the skis and the hat than before. If that's the case, then we expect the ground to be pushing up with 10 newtons of force. And if you allow me to make some assumptions here, let's pretend that there's not really much air resistance. Little potato, there's not a lot of wind. There really would be some, and that would be acting against this motion. So if we pretend that's not there, and there's no more other forces acting, this little potato could be cruising along to our right. This potato may actually be going this way. Whee! But the forces acting on it are just vertical forces. And again, the total force equals 0. So again, our little spud is in equilibrium. Okay, check out Newton's laws for what happens when things are in equilibrium, in particular Newton's first law.